Most people think the most terrifying places in the universe are the ones we can clearly identify. Black holes dominate our imagination. They swallow light, bend space itself, and possess gravity so intense that nothing crossing a certain boundary can ever return. They appear in films, novels, and documentaries as the ultimate expression of cosmic danger. If one were asked to point toward the most hostile region in existence, a black hole would seem the obvious answer, yet modern astronomy suggests a quieter possibility. The greatest mystery may not lie inside the darkest objects we know, but within the immense stretches of apparent nothingness that separate entire galaxies. Between the glowing islands of stars that fill our night sky exists an ocean so vast that even light requires millions of years to cross its narrowest channels and billions of years to traverse its widest reaches. These regions appear empty when viewed through almost every telescope humanity has ever built. They produce almost no visible light. They contain few stars. Often they seem to contain almost nothing at all. And yet, those silent expanses quietly determine how galaxies are born, how they evolve, and perhaps even how the entire universe will end. This presents an unexpected paradox. The places that appear least important may, in fact, govern everything around them. For centuries, empty space was regarded as little more than the stage upon which the drama of the cosmos unfolded. Stars lived and died, galaxies collided, black holes formed, planets circled their suns. Space itself simply provided room for these events to happen. But over the past 100 years, that comfortable picture has gradually dissolved. Astronomers have discovered that empty space is neither passive nor truly empty. Invisible matter bends the paths of light through regions where no stars exist. Extremely thin clouds of hot gas stretch across millions of light years, connecting galaxies like delicate strands in an unimaginably vast web. Quantum physics suggests that even the quietest vacuum may never become completely still. Meanwhile, the expansion of the universe appears driven not by galaxies themselves, but by something woven into the fabric of space between them. The more carefully scientists examine emptiness, the more complicated it becomes. Curiously, black holes themselves have contributed to this realization. They are extraordinary objects, but they occupy remarkably little of the universe. If every black hole vanished tomorrow, the overwhelming majority of cosmic space would remain almost exactly as it is now. The true landscape of the cosmos is not dominated by black holes, nor by stars, nor even by galaxies. Instead, it is dominated by distances, extraordinary distances. A single galaxy may contain hundreds of billions of stars, yet the gulf separating one galaxy from another is almost beyond comprehension. The Milky Way spans roughly 100,000 light-years. The neighbouring Andromeda galaxy lies about 2.5 million light-years away. Between them stretches an enormous darkness that, at first glance, seems almost entirely vacant. Multiply that separation across trillions of galaxies, and an astonishing picture begins to emerge. The visible universe is less like a crowded city than an immense archipelago, where luminous islands float upon an ocean so vast that its waters seem almost infinite. Oddly enough, this ocean refuses to behave like emptiness should. Light passing through it changes in subtle ways. Entire galaxies appear to move according to influences hidden within it. Massive structures spanning hundreds of millions of light-years grow because of forces operating largely beyond ordinary vision, even the oldest light in existence. The faint afterglow left behind shortly after the Big Bang carries delicate fingerprints from these seemingly empty regions. Every new generation of telescopes has made the darkness appear less simple. The Hubble Space Telescope revealed that galaxies gather into enormous filaments separated by giant voids. The Planck spacecraft measured tiny fluctuations in ancient radiation that trace the seeds from which these structures later emerged. Powerful radio observatories now detect incredibly diffuse gas drifting through intergalactic space. While sophisticated computer simulations suggest that much of the ordinary matter in the universe has spent billions of years hiding between galaxies rather than inside them, each discovery answers one question while quietly opening another. If space between galaxies contains matter, why is it so difficult to observe? If gravity shapes these regions, what unseen mass provides that pull? If empty space itself possesses energy, why does it accelerate the expansion of the cosmos? These are not philosophical puzzles. They arise directly from observation. Astronomy has become remarkably precise. Tiny shifts in the brightness of distant supernovae, minute distortions in the paths of light, and almost imperceptible variations in ancient microwave radiation all point toward the same conclusion. Something important occupies what once appeared empty, yet much of it remains invisible. This creates one of science's most remarkable situations. Humanity understands many violent objects with surprising confidence. We can describe the life cycles of stars, predict the motions of planets centuries into the future, and even detect the ripples produced when black holes collide billions of light years away. But the vast darkness filling most of the universe continues to resist complete explanation. In some ways, the greatest challenge in astronomy is no longer finding spectacular objects. It is understanding the quiet places between them. Perhaps this is why the space-separating galaxies inspires a different kind of wonder than black holes ever could. A black hole announces its presence through extraordinary gravity. Intergalactic space whispers. Its influence is subtle. Its appearance is deceptively calm. Its secrets reveal themselves only through patience, careful measurement, and decades of observation. The deeper astronomers look into that silence, the less certain they become that emptiness deserves its name at all. Before we can understand why these immense regions may be more mysterious than black holes, however, we must first return to the familiar picture of the cosmos that shaped generations of astronomers. Only then can we begin to see where that picture started to fracture. Only then can we appreciate how a universe once thought to be filled with isolated galaxies gradually transformed into something far stranger. Only then can we ask whether the greatest mystery in the cosmos is not what shines brightly across the heavens, but what quietly exists in the darkness between every point of light. When we step outside on a clear night, the universe appears full. Thousands of stars scatter across the sky, while a faint river of light, the Milky Way, stretches from one horizon to the other with the aid of a small telescope. Distant nebulae emerge as delicate clouds, and a handful of neighbouring galaxies become visible as pale smudges against the darkness. It is easy to conclude that the cosmos is densely populated, that wherever we look there is another star, another planet, another galaxy waiting just beyond the limits of our vision. In one sense, that impression is true. The observable universe contains hundreds of billions, and perhaps even trillions, of galaxies. Each galaxy may contain hundreds of billions of stars. Around many of those stars orbit planets, moons, comets, and countless smaller worlds. The total number of stars almost defies language. It exceeds the number of grains of sand on every beach on Earth by an enormous margin, and yet this remarkable abundance hides an equally remarkable emptiness. The stars are not crowded together. They are separated by extraordinary distances. Our own sun offers a useful place to begin. It feels close because its light reaches Earth in just over 8 minutes. On a human scale, 8 minutes seems insignificant, but light travels at nearly 300,000 kilometers every second. During those 8 minutes, it covers about 150 million kilometers. If the sun were replaced by another ordinary star at the same distance, our night sky would never become dark. Instead, the nearest star beyond our sun, Proxima Centauri, is over 4 light-years away. Light leaving its surface begins a journey lasting more than 4 years before reaching Earth. Even travelling at the fastest speed nature allows, it cannot arrive any sooner. Already the emptiness is beginning to reveal itself. Within our own stellar neighbourhood, the dominant feature is not stars. It is the vast space between them. The same pattern repeats on larger scales. Our solar system resides within one spiral arm of the Milky Way, itself a graceful disk roughly 100,000 light-years across. From a distance, it appears rich with glowing stars, colourful nebulae, and dark lanes of interstellar dust. But if someone could shrink the entire galaxy until it measured the width of North America, each individual star would still be separated by distances comparable to hundreds of kilometers. Even inside galaxies, emptiness greatly outweighs substance. The beautiful spiral arms seen in astronomical photographs are not solid structures. They are loose patterns containing immense gaps. Most of a galaxy consists not of stars packed tightly together, but of astonishingly thin gas and nearly unimaginable stretches of open space. This is fortunate, because stars are so widely separated. Direct collisions between them are extraordinarily rare. Entire galaxies can pass through one another during mergers involving hundreds of billions of stars, and yet very few stars ever collide directly. Gravity reshapes their orbits. Gas clouds compress and ignite new generations of stars. But individual suns usually slip past one another untouched. The universe is far more spacious than our everyday intuition allows. Our intuition evolved on Earth, where empty space is uncommon. A forest appears dense because trees grow only meters apart. Cities feel crowded because buildings stand side by side. Even the atmosphere around us contains trillions of molecules in every cubic centimeter. By contrast, interstellar space often contains only a few atoms within an entire cubic centimeter. In the emptiest regions between galaxies, even those lonely atoms become increasingly scarce, as astronomers gradually expanded their view beyond the Milky Way. This realization became even more profound. For much of human history, our galaxy was believed to encompass nearly everything that existed. The faint spiral nebulae visible through early telescopes were thought to be clouds of gas within the Milky Way itself. It was not until the early 20th century that careful observations revealed their true nature. They were galaxies, entire stellar systems comparable to our own. Suddenly the universe grew by an almost incomprehensible factor. The Milky Way was no longer the whole cosmos. It was simply one member of a much larger family. The nearest large member of that family is the Andromeda Galaxy, to the naked eye under exceptionally dark skies. Andromeda appears as a faint oval patch scarcely larger than a distant cloud. Yet that small blur contains roughly 1 trillion stars and stretches more than 200,000 light-years across. Despite its enormous size, Andromeda remains separated from the Milky Way by approximately 2.5 million light-years. The galaxies themselves are immense. The distance between them is greater still. This ratio repeats across the observable universe. Galaxy groups combine into clusters. Clusters assemble into superclusters. Each larger structure contains increasing amounts of empty space. At first glance, this arrangement appears almost accidental, as though galaxies were scattered randomly across an endless cosmic sea. For decades, many astronomers pictured the universe in precisely this way. Galaxies seem like isolated islands floating independently through otherwise featureless darkness. It was a comforting image. Simple, orderly, easy to understand. If one could somehow travel far enough beyond the Milky Way, perhaps the journey would become monotonous. One galaxy would slowly fade behind while another gradually appeared ahead. Separated by enormous but essentially uneventful distances, the darkness between them would merely be empty. Nothing more. This picture fit comfortably within the scientific understanding of its time. Gravity explained the motions of planets. Stars generated light through nuclear fusion. Galaxies orbited within clusters. Space itself served as the quiet stage upon which these events unfolded. There seemed little reason to suspect that the stage possessed important properties of its own. Yet astronomy has often advanced by questioning its simplest assumptions. The history of science is filled with familiar ideas that survived for centuries before subtle observations exposed tiny inconsistencies. At first, Those inconsistencies seemed almost trivial. They were small enough to overlook, easy to dismiss as measurement errors or incomplete data. Only later did they reveal entirely new ways of seeing reality. The familiar picture of galaxies floating through empty darkness would prove no exception. The first hints arrived quietly. Astronomers noticed that galaxies were not distributed as evenly as expected. Some regions contained rich collections of galaxies gathered together in vast clusters. Other regions appeared strangely deserted. As telescopes improved, these patterns became increasingly difficult to ignore. The universe was beginning to display a hidden architecture. The apparent emptiness separating galaxies was not arranged randomly. Something larger was organizing it. Something invisible seemed to shape where galaxies formed, where they gathered and where they did not. The comfortable image of isolated islands drifting upon a featureless sea was beginning to crack. The darkness itself appeared to possess a pattern, and once astronomers recognized those first faint signs of order, they realized they would need to redraw the map of the universe from the beginning. Every great scientific discovery begins in much the same way. Not with an answer, but with a small discomfort. The familiar explanation continues to work almost everywhere. Yet somewhere along the edge of observation, tiny details refuse to fit. At first they appear insignificant, perhaps the result of imperfect instruments or incomplete measurements. Most disappear as technology improves, a few do not. Astronomy has experienced this pattern many times. The planets did not move exactly as expected until a deeper understanding of gravity emerged. Starlight revealed hidden chemical elements long before scientists could reproduce those conditions on Earth. Even the realization that the universe is expanding began as a handful of measurements that seemed slightly too consistent to ignore. The same quiet process unfolded as astronomers studied the largest structures in the cosmos. If galaxies had formed independently throughout an otherwise uniform universe, their positions should have appeared roughly random. Some clustering would naturally occur because gravity pulls neighboring galaxies together over billions of years. But randomness still has recognizable statistical patterns. The universe refused to follow them. As larger surveys mapped increasing numbers of galaxies, strange arrangements began to emerge. Instead of being sprinkled evenly across space like grains of sand scattered over a table, galaxies gathered into long chains, broad sheets, and enormous concentrations. Between these crowded regions lay expanses containing remarkably few galaxies at all. The contrast was subtle at first. Early maps covered only tiny portions of the sky. Looking through them was like trying to understand the geography of an entire continent after exploring only a few villages. The gap seemed interesting but inconclusive. Then the maps grew larger. During the second half of the 20th century, astronomers measured the distances to thousands of galaxies with steadily improving precision. Every new observation added another point to an expanding three-dimensional picture of the nearby universe. Instead of becoming smoother, the pattern became more striking. Galaxies were not simply grouped into clusters. The clusters themselves appeared connected. Long bridges of galaxies stretched across hundreds of millions of light years. Vast empty regions occupied the spaces between these bridges. The larger the map became, the more obvious the hidden organization appeared. It resembled something surprisingly familiar. Not a collection of islands, not a cloud, but a network. The comparison emerged almost naturally. Viewed from a great distance, the distribution of galaxies resembled the delicate strands of a spider's web glistening with morning dew. Bright intersections marked regions where many galaxies gathered. Thin filaments connected these intersections across extraordinary distances. Between them opened immense dark chambers containing almost nothing visible at all. No one had expected the universe to organize itself in this way. The discovery raised an immediate question. What could create structures so enormous? Gravity offered part of the answer. Every galaxy attracts every other galaxy. Over immense spans of time, even incredibly weak gravitational forces gradually reshape the cosmos. Regions containing slightly more matter attract additional matter, growing denser as billions of years pass. But another puzzle quickly appeared. Gravity can only amplify differences that already exist. Where had those original differences come from? The early universe, according to observations of the cosmic microwave background, was astonishingly smooth. Temperature variations measured across the ancient radiation amount to only a few parts in 100,000. That is remarkably uniform. Yet somehow those tiny irregularities eventually evolved into structures spanning hundreds of millions of light years. It seemed almost impossible. A wrinkle barely visible in the infant universe had somehow become the largest architecture nature has ever produced. The question became even more intriguing when astronomers examined galaxy clusters more closely. Clusters are among the most massive gravitationally bound objects known. They contain hundreds or even thousands of galaxies orbiting a common center. Hot gas fills the space between those galaxies, glowing faintly in X-rays. Together they represent immense concentrations of matter. Yet careful calculations repeatedly produced an unsettling result. The visible matter was not enough. The galaxies moved too quickly. Their mutual gravity, based only on stars and gas that could actually be seen, should not have been sufficient to hold the clusters together. According to Newton's laws, many galaxies ought to have escaped long ago. Instead, they remained bound. Something unseen appeared to contribute additional gravity. This mystery did not arise from one observation alone. It appeared again and again. Different clusters, different telescopes, different methods, always the same conclusion. The cosmos seemed heavier than it looked. Meanwhile, another line of evidence emerged from an entirely different direction. According to Einstein's theory of general relativity, gravity bends the path of light itself. A massive object can act like a gigantic natural lens, distorting the images of more distant galaxies lying behind it. Astronomers began observing these gravitational lenses throughout the sky. Sometimes a distant galaxy appeared stretched into luminous arcs. Sometimes multiple images of the same galaxy surrounded an invisible foreground mass. By measuring the amount of bending, scientists could estimate the total gravity present. Again, the answer exceeded expectations. The visible galaxies accounted for only part of the effect. An unseen component appeared responsible for much of the remaining gravitational pull. These discoveries did not immediately solve anything. Instead, they deepened the mystery. The invisible mass became known as dark matter, not because it was literally dark in the ordinary sense, but because it neither emitted nor reflected detectable light. Whether dark matter consists of undiscovered particles or something even stranger remains one of modern physics' greatest unanswered questions. But regardless of its true nature, its influence seemed impossible to ignore. The hidden structure of the universe suddenly made more sense. Perhaps galaxies were tracing an invisible framework. Perhaps the luminous objects we observe are merely the visible highlights of a much larger gravitational skeleton extending throughout space. Computer simulations soon explored this possibility, starting with the tiny fluctuations observed in the early universe. Researchers allowed gravity to shape enormous virtual universes over billions of simulated years. The results were remarkable. Without any human guidance, intricate networks emerged. Filaments formed naturally. Dense intersections evolved into galaxy clusters. Immense empty regions appeared between them. The simulated universes began to resemble the real one with surprising accuracy. This did not prove every detail of the underlying model. Scientific models are judged by how well they explain observations, not by perfection. Yet the agreement was strong enough to suggest that astronomers were beginning to glimpse something profound. The largest structures in existence were not random accidents. They were the natural outcome of cosmic evolution, operating over nearly 14 billion years. Still, one detail remained deeply unsettling. If galaxies occupy the bright strands of this immense network, then what exactly fills the enormous regions between them? Are they truly empty, or are they simply too faint, too diffuse, or too unfamiliar for us to recognize? That question would lead astronomers beyond the galaxies themselves and toward one of the most astonishing discoveries ever made about the architecture of the universe. Some discoveries arrive in a single moment. A lone observation overturns an old belief, and history quietly divides itself into before and after. Others unfold so gradually that no one notices when the old picture has finally disappeared. The discovery of the cosmic web belonged to the second kind. No astronomer ever pointed a telescope toward one region of the sky and suddenly saw a vast network stretching across the universe. Instead, thousands of observations collected over decades slowly assembled into a picture that no individual observer could have imagined. Each new survey contributed another small piece. Only when enough pieces had accumulated did the hidden architecture reveal itself. By the middle of the 20th century, astronomers had become increasingly skilled at measuring the distances to galaxies. This was no simple task. Unlike stars within our own galaxy, distant galaxies cannot be reached by straightforward geometric methods. Instead, astronomers relied upon what is often called the cosmic distance ladder. Nearby objects helped calibrate slightly more distant ones, which in turn calibrated still more distant galaxies. Each rung of the ladder extended humanity's reach farther into space. Meanwhile, another remarkable tool had matured: the expansion of the universe. Nearly a century earlier, observations by Edwin Hubble and several contemporaries had demonstrated that almost every distant galaxy is moving away from us. More importantly, the farther away a galaxy lies, the faster it appears to recede. This relationship transformed astronomy. Instead of measuring every galaxy individually, astronomers could estimate enormous cosmic distances by carefully observing the stretching of light itself. As galaxies move away, the wavelengths of their light become slightly longer. Blue light shifts toward red. This phenomenon, known as redshift, became one of astronomy's most powerful measuring tools. With increasingly precise redshift measurements, astronomers could begin constructing three-dimensional maps rather than simple photographs of the sky. The difference was profound. A photograph compresses everything onto a flat surface. A three-dimensional map reveals depth. Objects that appear close together may actually lie hundreds of millions of light-years apart, while others separated across the sky might belong to the same enormous structure extending toward or away from Earth. As the first large maps emerged, something unexpected became impossible to overlook. Galaxies preferred company. They gathered into clusters far more often than chance alone would predict. That discovery itself was not surprising. Gravity naturally draws neighboring galaxies together. The surprise lay in what happened next. Clusters themselves refused to remain isolated. Instead, they connected to neighboring clusters through elongated chains of galaxies stretching across astonishing distances. One of the earliest glimpses of this larger organization came through painstaking surveys during the 1970s and early 1980s. Astronomers spent countless nights recording the positions and redshift of individual galaxies, one measurement at a time. Compared with today's automated observatories, the process was remarkably slow, yet patience often reveals patterns invisible to speed. In 1986, astronomers Margaret Geller and John Huckra published one of the most influential galaxy surveys ever produced, known informally as the CFA Redshift Survey Slice. It displayed the distribution of thousands of nearby galaxies in an elegant wedge extending outward from Earth. The results surprised almost everyone who saw it. Rather than appearing evenly distributed, galaxies traced enormous arcs and interconnected filaments surrounding surprisingly empty regions. One feature became particularly famous. An immense wall of galaxies stretched across roughly 500 million light-years. It became known simply as the Great Wall. The name was appropriate. At the time, no larger structure had ever been identified. The discovery forced astronomers to reconsider the scale of cosmic organization. If structures this enormous existed nearby, perhaps they continued throughout the observable universe. Subsequent surveys confirmed precisely that. Throughout the following decades, Increasingly ambitious projects mapped millions of galaxies. The 2-degree field galaxy redshift survey expanded humanity's view dramatically. Later, the Sloan Digital Sky Survey transformed astronomy once again by measuring the positions and distances of galaxies across vast portions of the northern sky. Each new map strengthened the same conclusion. The universe possessed an intricate large-scale architecture. Galaxies occupied dense intersections resembling cosmic cities. Filaments connected those cities across unimaginable distances. Between them stretched enormous regions containing remarkably few galaxies. The entire observable universe resembled a living network. The phrase cosmic web gradually entered astronomical language because no simpler description seemed adequate. The comparison was more than poetic. Computer analysis demonstrated that the resemblance to a web was mathematically meaningful. Nodes, filaments, sheets, voids, these became the vocabulary of large-scale cosmology. Yet another remarkable realization soon followed. The galaxies themselves represented only a tiny visible fraction of the web. The true structure extended far beyond what ordinary telescopes could easily observe. Evidence emerged from many independent directions. X-ray observatories detected extraordinarily thin gas filling the spaces between galaxies inside massive clusters. Radio telescopes found faint traces of hydrogen stretching across intergalactic distances. Gravitational lensing revealed concentrations of mass where relatively little visible matter existed. Most strikingly, computer simulations based on dark matter consistently predicted an even richer network than telescopes could directly detect. In these simulations, invisible dark matter formed the underlying scaffolding first. Ordinary matter then flowed slowly along its gravitational pathways, collecting within dense regions where galaxies eventually formed. It was rather like morning fog gathering within the valleys of an unseen landscape. The fog reveals the shape of the terrain, even though the terrain itself remains hidden beneath it. Galaxies, in this analogy, reveal the hidden contours of gravity. They do not create the landscape, they merely illuminate it. This realization transformed the role of galaxies. For centuries they had seemed like the principal actors of cosmic history. Now they appeared more like bright markers tracing something vastly larger and mostly invisible. The stars we admire occupy only the luminous tips of an immense cosmic framework. Most of the structure itself remains unseen. Perhaps even more remarkable was the scale. The cosmic web spans billions of light-years. Individual filaments may extend hundreds of millions of light-years before merging into even larger intersections. Some galaxy clusters contain masses equivalent to thousands of Milky Ways. The void separating these structures can exceed 100 million light-years across. Nothing constructed by stars approaches such dimensions. Even the largest galaxies become tiny by comparison. Human intuition struggles with these numbers because they possess no equivalent in everyday experience. Mountain ranges seem immense until viewed from orbit. Continents appear vast until compared with Earth itself. Likewise, galaxies feel enormous until placed within the context of the cosmic web. Then they become individual lights suspended upon an unimaginably larger framework. Yet the greatest surprise still lay ahead. If the filaments represented regions where matter accumulated, what exactly existed inside the immense void surrounding them? Were these vast chambers simply empty space, or did they conceal subtle forms of matter and energy that had not yet revealed themselves? Astronomers were about to discover that the darkest regions of the cosmic web were not merely gaps between galaxies. They were destinations worthy of study in their own right, and in many ways, they would prove even more mysterious than the brilliant structures surrounding them. The word void suggests absolute emptiness. It evokes the image of a perfect vacuum, a place where nothing exists, where not even a single atom interrupts the silence. In everyday language, a void is the absence of everything. In cosmology, however, the meaning is both more precise and more intriguing. A cosmic void is not completely empty. It is simply astonishingly underpopulated. That distinction may seem small at first, but it changes the way astronomers think about some of the largest regions in existence. The cosmic web, revealed through decades of galaxy surveys, resembles a vast network of luminous filaments surrounding enormous cavities. Those cavities are the voids. They are among the largest known structures in the observable universe. Some span 30 million light-years, others exceed 100 million. A few of the largest approach several hundred million light-years across. Even these numbers can be difficult to appreciate. If our entire Milky Way galaxy were reduced to the size of a single grain of sand, one of the larger cosmic voids would still be comparable to an entire continent. Scale, in the universe, has a way of quietly defeating imagination. Within a galaxy, stars are separated by light-years. Between galaxies, distances increase to millions of light-years. Between the great walls and filaments of the cosmic web, those separations become hundreds of millions. At every level, emptiness grows faster than matter. One of the best-known examples is the Butter's void. Discovered in 1981 while astronomers were mapping the large-scale distribution of galaxies, it occupies a region roughly 330 million light-years in diameter. Although not completely devoid of galaxies, it contains remarkably few. If the same average density found elsewhere in the universe existed inside the Butter's void, thousands more galaxies would be expected. Instead, only a sparse population inhabits this immense volume. It is often described as one of the loneliest places known. Yet even that description requires careful interpretation. Loneliness, from a human perspective, implies isolation. Cosmic voids are something altogether different. They are not isolated objects. They are essential parts of the universe's architecture. Without the voids, the filaments would not exist. Without the vast empty regions expanding between concentrations of matter, the intricate pattern of the cosmic web could never have emerged. The web and the voids define one another. One cannot exist without the other. This realization transformed the scientific importance of these seemingly empty places. For many years, astronomers concentrated almost exclusively on galaxies. After all, galaxies shine. They produce light across the electromagnetic spectrum. Stars reveal their temperatures, motions, and chemical compositions. Black holes betray themselves through their influence on nearby matter. Galaxies are rich with observable information. Voids appeared almost featureless, but as observations became increasingly sophisticated, researchers realized that the voids themselves contained valuable clues about how the universe evolves. In some respects, they function as natural laboratories. Inside dense galaxy clusters, gravity is extraordinarily complicated. Galaxies interact, gas collides, stars form, black holes grow. Many different physical processes occur simultaneously within a cosmic void. By contrast, the environment is much simpler. There are fewer galaxies, fewer gravitational disturbances, less energetic activity. The underlying expansion of the universe becomes easier to observe because fewer local influences interfere with it. The emptiest regions therefore provide some of the clearest opportunities to study the large-scale behavior of the cosmos itself. Another surprising characteristic gradually emerged. The voids are not static. Like everything else in the expanding universe, they evolve. In fact, they often grow larger over time. Gravity pulls matter toward the denser filaments and clusters surrounding each void. As galaxies and gas slowly migrate outward, the central regions become even emptier. It is a subtle process unfolding across billions of years. The rich become richer, the empty become emptier. This pattern appears naturally in computer simulations based on the standard cosmological model. Starting from the tiny density fluctuations present shortly after the Big Bang, gravity slowly amplifies the differences. Dense regions attract additional matter. Underdense regions lose matter to their surroundings. Over immense periods of time, the contrast sharpens. The cosmic web becomes increasingly pronounced. The voids expand, the filaments thicken. The universe organizes itself without any external designer, guided only by gravity acting upon the initial conditions of the early cosmos. Yet even here, another mystery quietly appears. If matter is constantly flowing out of the voids, Why do they contain anything at all? The answer reminds us that absolute emptiness remains surprisingly elusive. Even the largest voids contain traces of ordinary matter. Extremely diffuse hydrogen drifts through them. Occasional dwarf galaxies quietly orbit within their depths. Invisible dark matter appears to permeate them, although at much lower densities than in surrounding regions. And throughout these immense expanses, photons continue their endless journeys, crossing distances so great that civilizations may rise and disappear before a single beam completes its passage. The voids are empty only by comparison. Compared with galaxy clusters, they are nearly barren. Compared with perfect nothingness, they remain astonishingly rich. This distinction becomes even more important when we consider another remarkable property of intergalactic space. The vacuum itself is not merely a passive backdrop. According to quantum field theory, every region of space is permeated by fundamental fields. Even when no particles are present, those fields do not become perfectly silent. Tiny quantum fluctuations continue to occur. They cannot be eliminated completely. This does not mean that particles are constantly appearing in the everyday sense often portrayed in popular culture. Rather, it reflects the fact that the lowest possible energy state of quantum fields still possesses subtle physical properties. Even apparent emptiness has structure. Astronomers studying cosmic voids therefore confront two different meanings of empty space. On the largest astronomical scales, a void is a region containing remarkably little matter. On the smallest quantum scales, the vacuum itself remains an active physical entity. The two ideas belong to different branches of physics, yet both challenge the ancient belief that empty space is simply nothing. Perhaps the greatest lesson offered by the voids is one of perspective. When early astronomers searched the heavens, they naturally focused upon what they could see. Stars guided navigation, galaxies filled photographic plates, nebulae decorated the sky with colour. Darkness seemed to be little more than the absence of light. Modern cosmology has gradually inverted that perspective. Today, scientists recognize that the darkness is not merely what surrounds the luminous universe. It is the environment within which the entire cosmic story unfolds. The voids occupy most of the observable universe by volume. Galaxies, magnificent though they are, exist primarily along the boundaries. The vast majority of the cosmos consists of regions that appear almost empty. And yet these immense silent expanses continue to shape the motions of galaxies, the growth of cosmic structures, and perhaps even the ultimate fate of the universe itself. The deeper astronomers ventured into the great voids, the more they encountered an unsettling realization. The greatest mystery was no longer how little these regions contained. It was how much influence they seemed to possess despite appearing so empty. That contradiction would soon lead directly to one of the most profound questions in modern physics. What, exactly, does it mean for space itself to be empty for much of human history? The idea of empty space seemed wonderfully uncomplicated. Remove the stars, remove the planets, remove every grain of dust and every cloud of gas. What remains, it would seem, is simply nothing. The ancient Greek philosophers debated whether such perfect emptiness could even exist. Aristotle argued that nature abhorred a vacuum, believing that true emptiness was impossible. Centuries later, experiments gradually demonstrated that air itself could be removed from sealed chambers, creating what appeared to be empty space. By the 17th century, the vacuum had become a physical reality rather than a philosophical argument. Yet every advance in physics since then has made the vacuum increasingly difficult to define. Today, astronomers and physicists no longer ask only what occupies space. They ask what space itself may be. This distinction lies at the heart of one of the deepest mysteries in modern science. When astronomers describe the vast regions between galaxies, they are not simply referring to enormous distances. They are referring to an environment whose fundamental nature remains surprisingly uncertain. At first glance, intergalactic space appears almost perfectly empty. Its average density is extraordinarily low. In many regions, a cubic meter contains fewer particles than the best laboratory vacuums ever created on Earth. If one could somehow drift through such a place, there would be almost nothing to see. No nearby stars, no glowing nebulae, no planets, only scattered atoms separated by enormous distances and the faint glow of distant galaxies that themselves might be millions of light years away. By every ordinary standard, it is emptiness. And yet modern physics quietly disagrees. The first hints emerged through the development of quantum mechanics during the early 20th century. Unlike classical physics, quantum theory does not describe particles as isolated objects moving through an otherwise inactive stage. Instead, every type of particle is associated with a quantum field extending throughout all of space. There is an electron field, a photon field, fields associated with quarks, neutrinos, and many other fundamental particles. These fields exist everywhere, not merely inside stars, not only within galaxies, everywhere. Even regions containing no detectable particles remain permeated by these underlying fields. This immediately changes the meaning of a vacuum. An empty region is no longer a place where absolutely nothing exists. It's a place where no particles are currently being observed, while the fields themselves remain present. An analogy can help, although like all analogies it has limits. Consider the surface of a calm lake at dawn. From a distance, the water appears perfectly still, yet close inspection reveals tiny ripples caused by gentle breezes, insects touching the surface, or subtle currents beneath. The lake is quiet, but not completely motionless. Quantum fields behave in a somewhat similar way. Even in their lowest possible energy state, they are not perfectly inactive. Tiny fluctuations remain. These fluctuations are not evidence that the vacuum is unstable or chaotic. Rather, they are consequences of the mathematical structure of quantum mechanics itself. One important point deserves careful emphasis. Popular descriptions often say that particles constantly pop into existence from nothing. While this phrase captures public imagination, it can easily become misleading. The quantum vacuum is not literally creating ordinary particles that suddenly appear and disappear like tiny fireworks. Instead, the theory predicts subtle temporary fluctuations in the fields that influence measurable physical phenomena. Scientists describe these effects using sophisticated mathematical models that have repeatedly matched experimental observations with extraordinary precision. The details remain complex, but the central lesson is remarkably simple. The vacuum possesses physical properties. It is not mere absence. This realization became increasingly important as physicists investigated how light and matter behave under extreme conditions. Certain laboratory experiments revealed tiny effects that could only be explained if the vacuum itself participated in physical processes. One famous example is the Casimir effect, when two extremely smooth metal plates are placed astonishingly close together inside a high vacuum. A minute attractive force appears between them. The effect is extraordinarily small and technically challenging to measure, yet repeated experiments have confirmed its existence with increasing accuracy. The explanation involves the behavior of quantum fields in the narrow space between the plates. The vacuum itself contributes to the measurable force. Nothing visible occupies the gap. Yet the gap is not physically empty. For cosmologists, discoveries like these carried profound implications. If the vacuum possesses energy on microscopic scales, could that energy influence the universe on its larger scales? This question would eventually lead to one of the greatest unsolved problems in theoretical physics. The difficulty is not that vacuum energy appears impossible. The difficulty is that different calculations predict astonishingly different values. Quantum field theory suggests one enormous amount. Astronomical observations indicate something incomparably smaller. The disagreement is so vast that it has become known as the cosmological constant problem, one of the most significant unresolved questions in modern science. No accepted solution yet exists. This is where astronomy and particle physics unexpectedly converge. The immense spaces between galaxies contain so little ordinary matter that the properties of space itself become increasingly important. Inside a star, overwhelming densities dominate everything. Inside a galaxy, gravity from billions of stars shapes local motion. But within the great cosmic voids, where matter becomes remarkably sparse. The underlying characteristics of space may become easier to study. It is almost as though the universe has prepared enormous natural laboratories extending across hundreds of millions of light years. The quieter the environment becomes, the more subtle effects begin to emerge. This realization gradually transformed cosmology. Astronomers no longer viewed intergalactic space as merely the distance separating galaxies. Instead, they began treating it as an active component of the universe, something with measurable properties, something capable of influencing cosmic evolution, something that deserved investigation in its own right. Yet another mystery soon complicated the picture. Even after accounting for ordinary matter and the invisible dark matter inferred from gravity, the observed expansion of the universe still refused to behave exactly as expected. Instead of slowing under gravity's influence, the expansion appeared to be accelerating. Galaxies were not merely moving apart. The very fabric of space between them seemed to be stretching faster as time passed. The discovery surprised cosmologists because it suggested that the largest influence on the universe might not reside inside galaxies at all. It might reside within the emptiness surrounding them. The vacuum, once regarded as the simplest concept in physics, had become one of its most mysterious. Empty space contained quantum fields. It possessed measurable physical properties. It appeared connected to the expansion of the cosmos. And despite decades of research, scientists still could not fully explain why. The farther astronomy ventured into the apparent nothingness between galaxies, the more it encountered unanswered questions instead of empty silence. Perhaps the greatest mystery was no longer whether space contained something. It was whether that something had quietly shaped the history of the entire universe from the very beginning. To answer that question, astronomers would have to follow the evidence itself, allowing light, gravity, and the oldest signals in the cosmos to reveal what human eyes could never directly see. Science advances most confidently when it follows evidence rather than expectation. The history of astronomy is filled with ideas that seemed perfectly reasonable until the universe quietly revealed something different. Earth once appeared to rest at the center of creation because every sunrise and sunset seemed to confirm it. The Milky Way was once believed to encompass the entire cosmos because nothing larger had yet been recognized. Even the notion that empty space was simply empty survived for centuries because no observation appeared to contradict it. Each belief gave way only when evidence accumulated patiently enough that the older picture could no longer contain it. The mystery of intergalactic space has unfolded in much the same manner. No single telescope has ever photographed the hidden structure of empty space in its entirety. Instead, astronomers have learned to read indirect clues, much as a geologist reconstructs an ancient landscape from scattered layers of rock. Cosmologists reconstruct the invisible universe from the subtle traces it leaves behind. One of the most powerful clues comes from light itself. Light is remarkably faithful. Once emitted by a distant galaxy, it travels through the cosmos carrying an extraordinarily detailed record of everything it encounters along the way. It may pass through hot gas, skim the edge of a galaxy cluster, cross a vast cosmic void, or thread its way along the filaments of the cosmic web. Each encounter leaves a small signature. None is dramatic. Together they tell a remarkable story. Consider the light from a quasar. Quasars are among the brightest persistent objects in the observable universe. At their centers lie supermassive black holes feeding upon enormous quantities of gas. As matter spirals inward, tremendous amounts of energy are released, making quasars visible across billions of light years. Their brilliance makes them ideal cosmic beacons. Between a distant quasar and Earth lies an immense journey through intergalactic space. Although that space appears empty, it is not completely transparent. Occasionally, the quasar's light passes through an extremely thin cloud of hydrogen gas drifting between galaxies. Hydrogen atoms absorb very specific wavelengths of light. When astronomers spread the quasar's light into a spectrum, they discover countless narrow absorption lines. Each line marks a cloud that the light encountered during its long voyage. These delicate patterns form what is known as the Lyman alpha forest. The name is wonderfully descriptive. Instead of seeing a single absorption feature, astronomers observe hundreds, sometimes thousands, of tiny lines packed closely together. They resemble the trunks of a dense forest. Each tree represents a cloud so diffuse that it would be almost impossible to detect by any other means. Individually, these clouds contain astonishingly little material. Collectively, they reveal that the space between galaxies is threaded with vast amounts of hydrogen spread across unimaginable distances. The discovery answered one question. Intergalactic space was not truly empty, but it immediately raised another. Why was the hydrogen arranged this way? Computer simulations offered a compelling explanation, as ordinary matter responded to the gravitational influence of dark matter. Gas gradually flowed into the same immense filaments predicted by cosmological models. The Lyman alpha forest therefore became something remarkable. It allowed astronomers to map structures that could not be photographed directly. The invisible landscape revealed itself through the light of faraway quasars. Another line of evidence arrived from a completely different source. Gravity, according to Einstein's general theory of relativity, mass curves space-time. Light follows those curves. As a result, massive objects act as natural gravitational lenses. Sometimes the effect is spectacular. A distant galaxy appears stretched into luminous arcs around a foreground cluster. Multiple images of a single quasar appear separated across the sky. These dramatic examples capture public attention because they are visually striking. But the most informative form of gravitational lensing is often far subtler. Known as weak gravitational lensing, it slightly distorts the shapes of millions of distant galaxies. No individual distortion proves very much. Galaxies naturally possess many shapes. Some are round, others are elongated. Viewed one at a time, the effect is almost impossible to recognize. But when astronomers analyze millions of galaxies statistically, a coherent pattern emerges. Tiny systematic distortions reveal where invisible mass bends space-time. The result is extraordinary. Scientists can construct maps showing the distribution of matter, including matter that emits no light whatsoever. Again and again, the maps reveal the same hidden framework. Dark matter outlines enormous filaments connecting galaxy clusters across the observable universe. Visible galaxies merely occupy the brightest intersections. The underlying gravitational skeleton extends much farther. Yet another source of evidence comes from perhaps the oldest light of all, about 380,000 years after the Big Bang. The young universe cooled enough for electrons and protons to combine into neutral hydrogen. For the first time, light could travel freely across space. That ancient radiation still fills the cosmos today. It is known as the cosmic microwave background, discovered accidentally in 1965 by Arno Penzias and Robert Wilson. It represents the oldest light humanity can observe directly. To the naked eye, it would appear perfectly uniform. Sensitive satellites, however, have revealed minute variations in its temperature. These differences amount to only a few millionths of a degree. They are extraordinarily small, yet they contain the seeds of everything that followed. Regions that were ever so slightly denser possessed slightly stronger gravity. Over billions of years, those tiny differences attracted additional matter. Galaxies formed, clusters emerged, filaments stretched across space, voids emptied. The magnificent cosmic web visible today grew from fluctuations so subtle that they can scarcely be measured. Modern observatories such as the Wilkinson Microwave Anisotropy Probe and later the Planck mission mapped these fluctuations with astonishing precision. Their measurements agree remarkably well with large-scale simulations of cosmic evolution, although many details remain uncertain. The broad picture has become increasingly consistent. The evidence does not come from one experiment. It comes from many. Quasar spectra, gravitational lensing, galaxy surveys, the cosmic microwave background, X-ray observations of hot intergalactic gas, radio telescopes tracing neutral hydrogen. Each method relies upon different instruments, different physical principles, and different forms of analysis. Yet they converge upon the same conclusion. The immense spaces between galaxies possess structure. Not obvious structure, not visible structure, but measurable structure. This convergence is one of science's greatest strengths. Confidence does not arise because a single observation appears convincing. It grows because independent observations, each vulnerable to different errors, repeatedly support the same underlying picture. Even so, careful scientists distinguish between what has been observed and what remains uncertain. The cosmic web is supported by overwhelming evidence. The existence of dark matter is strongly supported by multiple independent observations. Although its fundamental nature remains unknown, the expansion of the universe is directly measured. Its acceleration is well established. The ultimate explanation for that acceleration remains an open question. In astronomy, certainty and mystery often coexist. The farther evidence carries us, the more clearly we recognize both what we understand and what still lies beyond our reach. By patiently following light across billions of years, by measuring tiny distortions almost invisible to the eye, and by listening to the oldest radiation in existence, astronomers have uncovered a universe whose empty spaces are anything but simple. Yet these discoveries present an unavoidable challenge. If so many observations point toward the same hidden reality, how should that reality be interpreted? Different theories offer different answers. Some fit comfortably within established cosmology. Others explore possibilities still awaiting decisive evidence. The next step is not to choose among them too quickly, but to examine each with equal care, separating what is known from what is merely possible. When confronted with a mystery, science does something remarkably simple. It resists the temptation to settle upon the first satisfying answer. Instead, it gathers every explanation that remains consistent with the evidence, tests each one as rigorously as possible, and gradually eliminates those that fail. The process can be slow, sometimes spanning decades or even generations, but it is precisely this patience that allows scientific understanding to become increasingly reliable. The mystery of intergalactic space is no exception. Over the past century, astronomers have assembled an extraordinary collection of observations. Galaxies cluster into vast filaments. Light bends more strongly than visible matter alone can explain. The universe continues to expand, and that expansion is accelerating. Enormous voids occupy most of cosmic volume, while invisible influences appear to shape their evolution. These observations are widely accepted. Their interpretation is where the discussion becomes more complex. To understand the current state of cosmology, it is helpful to separate four different categories: observed facts, measured evidence, accepted theories, open hypotheses. Although they often become blurred in popular discussions, scientists work carefully to distinguish among them. Let us begin with what belongs firmly in the first category. It is an observed fact that galaxies are not randomly distributed throughout space. Large astronomical surveys repeatedly reveal clusters, filaments, walls, and immense voids. This pattern has been confirmed by independent observatories across several decades. Likewise, it is an observed fact that distant galaxies exhibit redshift, indicating that the universe is expanding. It is also an observed fact that the expansion is accelerating, based upon careful measurements of distant Type Ia supernovae, together with supporting observations of the cosmic microwave background and large-scale structure. Another observed fact is gravitational lensing. Light from distant galaxies is bent exactly as Einstein's general relativity predicts when sufficient mass lies along its path. The bending itself is directly measured. These are not assumptions. They are observations. The next category is measured evidence. Unlike direct observations, evidence requires interpretation, though usually in a straightforward way. When astronomers measure the motions of galaxies inside clusters, they consistently find more gravity than visible matter can provide. When they analyze gravitational lensing, they infer additional unseen mass. When they simulate the evolution of cosmic structure, Models containing this unseen matter reproduce many observed features with remarkable success. This evidence strongly suggests that a substantial fraction of the universe consists of matter that neither emits nor absorbs detectable light. That conclusion enjoys broad scientific support. Yet notice an important distinction. Astronomers observe gravity. They infer dark matter. No telescope has directly photographed a dark matter particle. Its existence is inferred because it explains many independent observations simultaneously. This distinction matters because science always remains open to better explanations if future evidence demands them. The third category contains accepted theories. Among the most successful is the lambda cold dark matter model, often abbreviated as lambda CDM. It serves as the standard model of modern cosmology. The name contains two important ingredients. Cold dark matter refers to invisible matter moving relatively slowly compared with the speed of light during the early stages of cosmic evolution. Its gravity provides the scaffolding upon which galaxies and the cosmic web gradually form. The Greek letter lambda represents the cosmological constant, a mathematical term originally introduced by Einstein and now commonly associated with dark energy, the phenomenon apparently responsible for the accelerating expansion of the universe. Together, these components describe a cosmos composed of roughly 5% ordinary matter, about 27% dark matter, and approximately 68% dark energy. These percentages are not arbitrary guesses. They emerge from multiple independent observations that fit together with impressive consistency. The lambda CDM model successfully explains a remarkable range of phenomena. The large-scale distribution of galaxies, the temperature fluctuations of the cosmic microwave background, the growth of galaxy clusters, the expansion history of the universe. Few scientific theories have matched so many observations across such enormous scales. And yet success does not mean completeness. Important questions remain unanswered. What exactly is dark matter? No confirmed particle has yet been detected despite decades of increasingly sensitive experiments. Numerous candidates have been proposed, weakly interacting massive particles, axions, sterile neutrinos. Other possibilities continue to be explored. Each has strengths. Each faces challenges. None has yet received decisive experimental confirmation. Dark energy presents an even deeper puzzle. Its existence is inferred from observation, but its physical nature remains obscure. If it represents vacuum energy, why does its measured value differ so dramatically from many theoretical predictions? If it is not vacuum energy, then what is it? Some researchers investigate dynamic fields that evolve over cosmic time. Others explore modifications to gravity itself. No explanation has yet achieved universal acceptance. This brings us to the final category, open hypotheses. Here the scientific landscape becomes broader, though also more uncertain. One family of ideas asks whether Einstein's theory of gravity remains perfectly accurate across the largest distances in the universe. General relativity has passed every experimental test performed within the solar system and many beyond it. Yet some physicists investigate whether subtle modifications might appear only across billions of light years, if gravity behaves slightly differently on cosmic scales. Perhaps some observations attributed to dark matter or dark energy could instead reflect incomplete knowledge of gravity itself. These ideas remain active areas of research. Another hypothesis explores whether the properties of dark energy change over time, rather than remaining constant throughout cosmic history. Perhaps its influence slowly evolves. Future astronomical surveys may eventually distinguish between these possibilities. Still, other proposals examine whether our understanding of the earliest moments after the Big Bang requires refinement. Tiny differences in the infant universe might have influenced the later formation of the cosmic web in ways not yet fully appreciated. Again, these remain hypotheses rather than established conclusions. What is striking about modern cosmology is not that scientists disagree. Disagreement, when grounded in evidence, is one of science's greatest strengths. Researchers often reach broad agreement about observations while debating their deeper interpretation. That distinction keeps the search honest. It prevents confidence from becoming certainty before the evidence is ready. The space between galaxies illustrates this beautifully. Nearly every astronomer agrees that these immense regions influence the evolution of the universe. The debate concerns precisely how they do so. Are they shaped primarily by dark matter? Does dark energy govern their long-term behavior? Could new physics emerge only within these extraordinarily low-density environments? Or will future observations reveal that several of these ideas are simultaneously correct? No single answer has yet prevailed, and perhaps that is exactly what makes this moment in astronomy so fascinating. For the first time in history, humanity possesses observations precise enough to reveal the hidden architecture of the cosmos, yet not precise enough to explain every part of it. The map has become astonishingly detailed. The legend that explains the map is still being written. The natural question, then, is this: if one of these interpretations proves correct, how differently would we need to think about empty space itself, and about the future evolution of the entire universe? Suppose, for a moment, that the quietest places in the universe are not merely the absence of matter. Suppose that empty space itself possesses properties that actively influence the evolution of the cosmos. This idea may sound unfamiliar, even counterintuitive. Our everyday experience teaches us that space is simply where objects happen to be. A room remains the same whether it is filled with furniture or completely empty. Remove everything inside it, and only the room remains. But nature often behaves differently on cosmic scales. The universe has repeatedly demonstrated that concepts which appear straightforward in ordinary life become surprisingly subtle when stretched across billions of light years. Modern cosmology invites us to consider precisely such a possibility, not because it is philosophically appealing, not because it is mysterious, but because observations increasingly suggest that the large-scale behavior of the universe cannot be explained by visible matter alone. Let's begin with a simple observation. Nearly every galaxy outside our local group is moving away from us. This does not mean Earth occupies a special location. Observers in almost any galaxy would see much the same pattern. The expansion occurs everywhere at once. An analogy, although imperfect, can be helpful. Imagine small dots resting upon the surface of a slowly expanding sheet of rubber. As the sheet stretches, every dot sees every other dot moving farther away. No dot occupies the center of the expansion. The sheet itself grows. Likewise, according to general relativity, galaxies are not primarily traveling through pre-existing space. Rather, space between them is expanding. This distinction is subtle but essential. When astronomers describe the expansion of the universe, they are describing changes in space-time itself. For billions of years after the Big Bang, gravity worked against this expansion. Matter attracts matter. Every galaxy, every cloud of gas, every concentration of dark matter contributed to a gentle cosmic braking force. If gravity alone governed the universe, one would expect the expansion gradually to slow. For much of the 20th century, astronomers assumed exactly that. The remaining question concerned only the rate of deceleration. Would gravity eventually halt the expansion? Would it reverse it entirely, producing a future collapse sometimes called the Big Crunch? Or would the expansion continue forever, while becoming steadily slower? These possibilities seem to encompass every reasonable future. Then observations introduced an unexpected complication. During the late 1990s, two independent international research teams studied extremely distant Type Ia supernovae. These stellar explosions serve as what astronomers call standard candles, because their intrinsic brightness is remarkably consistent. They allow researchers to estimate enormous cosmic distances with considerable precision. The goal appeared straightforward: measure how rapidly the expansion had slowed over billions of years. Instead, the data pointed somewhere entirely different. The distant supernovae appeared slightly dimmer than expected. The simplest interpretation was extraordinary, rather than slowing down. Cosmic expansion had been accelerating. The galaxies were separating faster with time. This conclusion emerged cautiously. Extraordinary claims demand extraordinary scrutiny. Independent measurements were repeated, alternative explanations were examined, instrumental errors were investigated, as additional evidence accumulated from the cosmic microwave background, galaxy surveys, and gravitational lensing. Confidence steadily increased. Today, the accelerating expansion is regarded as one of the central observational discoveries of modern cosmology. What causes it remains uncertain. One possible explanation involves the energy associated with empty space itself. If the vacuum possesses a small but persistent energy density, then every cubic meter of space contributes a tiny amount. Individually, that contribution would be almost unimaginably small. Collectively, spread across the immense volume of the observable universe, it becomes significant. As space expands, more space exists. If the energy density remains approximately constant, then the total vacuum energy increases as the universe grows. This is a deeply unfamiliar idea. It challenges everyday intuition because ordinary experience rarely involves expanding space. Yet mathematically, it fits remarkably well within Einstein's equations. The cosmological constant, once introduced and later abandoned by Einstein, returned to cosmology with renewed importance. Whether it truly represents vacuum energy remains one of the great unanswered questions, but its observational consequences resemble what astronomers measure. Now consider one possible implication. If empty space possesses intrinsic properties independent of galaxies, then the largest structures in the universe become governed less by the matter they contain and more by the space surrounding them. Over sufficiently long timescales, galaxies gradually drift farther apart. Galaxy clusters remain gravitationally bound because their internal gravity overwhelms cosmic expansion. Beyond those clusters, however, the growing distances continue to increase. The cosmic web itself slowly stretches. The great voids expand. Filaments become increasingly isolated. The universe grows not merely older, but lonelier. Computer simulations based on the standard cosmological model suggest precisely this gradual evolution. Nothing dramatic occurs over a human lifetime. Even across millions of years, the changes remain almost imperceptible. But given tens of billions or trillions of years, the transformation becomes profound. Many galaxies beyond our local group will eventually recede so rapidly due to the expansion of space that their light will never again reach future observers in our region of the universe. This is not because those galaxies travel through space faster than light. Special relativity remains intact. Instead, the space between distant regions continues expanding. The increasing separation prevents later light from ever bridging the growing gap. Future astronomers, living trillions of years from now inside the merged remnant of the Milky Way and Andromeda, might observe a dramatically different sky. Most distant galaxies could disappear beyond the observable horizon. Evidence for the expanding universe itself might become extraordinarily difficult to detect. Ironically, they could inhabit a universe appearing far smaller than the one we observe today. This possibility illustrates how profoundly the properties of empty space influence cosmic history. The stars themselves needn't change first. The galaxies need not vanish immediately. The transformation begins quietly within the expanding darkness separating them. Still, important caution is necessary. This picture follows naturally if the standard cosmological model remains correct and if dark energy behaves approximately as observations currently suggest. Alternative possibilities continue to be investigated. Dark energy may evolve over time. Gravity could behave differently on the larger scales. Future observations might require revisions to today's understanding. Science remains open to those possibilities because evidence, not preference, ultimately decides. Yet even within our present framework, one conclusion already stands. The vast regions between galaxies are not passive scenery. They participate in shaping the future of the observable universe. What once appeared to be the least interesting component of the cosmos now influences its largest patterns and its longest destiny. Curiously, this realization also changes the way we think about galaxies themselves. Perhaps they are not the principal characters after all. Perhaps they are travelers carried along by an even greater story unfolding within the quiet fabric of space. And if that is true, another question naturally follows. How deeply are the galaxies, black holes, and the invisible framework of dark matter connected by the same underlying cosmic architecture by now? The familiar picture of the universe has changed almost beyond recognition. We began with stars scattered across the night sky and galaxies separated by immense darkness. Gradually, those galaxies became part of an intricate cosmic web. The darkness between them revealed traces of gas, invisible matter, quantum fields, and the steady expansion of space-time itself. Yet an even larger perspective still awaits. The universe is not simply a collection of objects. It is a system. Every galaxy, every filament, every void, and every cluster participates in an ongoing evolution that has lasted for nearly 14 billion years. To understand why the space between galaxies may be more significant than the galaxies themselves, we must zoom outward once again, not by a factor of 10, nor by 100, but until entire superclusters become individual points upon an almost unimaginable map. Human beings naturally think in terms of neighborhoods. Our solar system feels enormous because the planet's occupied distance is measured in billions of kilometers. The Milky Way feels almost incomprehensible because it stretches across 100,000 light years. Yet on the largest cosmological maps, the Milky Way barely registers. It becomes one tiny member of a modest collection known as the local group. The local group contains more than 100 galaxies, although most are small dwarf galaxies orbiting three dominant members of the Milky Way, Andromeda and the Triangulum galaxy. These galaxies are not isolated. Gravity binds them together. Over billions of years, they dance around one another in slow, graceful motion. In roughly 4 to 5 billion years, the Milky Way and Andromeda will merge, forming a single larger galaxy. From the perspective of individual stars, the event will be surprisingly gentle. The vast distances separating stars mean that direct stellar collisions remain exceedingly unlikely. Gravity will reshape the galaxies without creating widespread destruction. Even this dramatic merger, however, represents only a local event. Beyond the local group lies something larger. Nearby galaxy groups combine into the Virgo cluster, a massive collection containing well over 1,000 galaxies. The Virgo cluster itself spans several million light-years and possesses enough gravity to influence the motions of surrounding groups, including our own, for decades. Astronomers viewed clusters like Virgo as some of the largest meaningful structures in existence. Then the maps grew again. Clusters themselves proved to be connected. The Virgo cluster belongs to an even larger arrangement called the Laniakea supercluster. The name comes from the Hawaiian language and may be translated as immense heaven, an appropriate description for a structure extending across roughly 500 million light-years. Within Laniakea reside approximately 100,000 galaxies, yet even this extraordinary structure does not possess sharply defined boundaries. Galaxies continue flowing along the filaments of the cosmic web, responding to gravity across astonishing distances. The farther astronomers expanded their maps, the less the universe resembled isolated objects and the more it resembled flowing currents. Matter does not simply exist. It moves, very slowly, very steadily. Over billions of years, galaxies drift along invisible gravitational pathways, gradually gathering where filaments intersect. These intersections become galaxy clusters. Clusters merge into larger concentrations. Meanwhile, matter slowly drains away from the great void separating them. The cosmic web is therefore not a frozen structure. It is an evolving one. Computer simulations illustrate this beautifully. Beginning shortly after the Big Bang, tiny density differences gradually strengthen. Dark matter forms an invisible network. Ordinary gas follows its gravitational pull. The first stars ignite. Young galaxies emerge. Over billions of years, filaments thicken while voids expand. The universe becomes increasingly organized without ever losing its overall expansion. Watching such simulations is rather like observing frost spread across a window pane. Delicate patterns emerge almost spontaneously. Individual branches connect into larger networks. No central planner directs the process. Simple physical laws operating patiently across immense spans of time generate extraordinary complexity. This perspective reveals something unexpected. Galaxies are not independent islands choosing their own locations. They are products of their environment. A galaxy forming inside a dense filament experiences a very different history from one born near the edge of a great void. Dense regions provide abundant gas, galaxies collide more frequently. Black holes encounter fresh material to consume. New stars continue forming. Within the sparse interior of cosmic voids, conditions are altogether quieter. Galaxies there tend to remain smaller. Interactions occur less often. Evolution proceeds more slowly. Location matters, not because space possesses different physical laws from place to place, but because the large-scale distribution of matter shapes every local environment. Astronomers sometimes describe this as cosmic ecology. Just as forests, deserts, mountains, and oceans create different habitats on Earth, the cosmic web creates different environments for galaxies. Some flourish within crowded intersections. Others spend billions of years in relative isolation. The architecture of the universe quietly influences their entire histories. Even supermassive black holes reflect this larger perspective. At first glance, black holes appear to dominate their host galaxies through overwhelming gravity. That is true locally, yet black holes themselves depend upon their surroundings. Galaxies growing inside dense regions acquire more gas through repeated mergers and gravitational interactions. That gas eventually feeds central black holes. The largest black holes therefore owe part of their existence to the cosmic web that channels matter toward them across enormous distances. In a subtle sense, the immense emptiness between galaxies helps determine how the brightest quasars shine. The influence runs deeper still. Chemical elements forged inside stars eventually escape through stellar winds and supernova explosions. Some of that material leaves galaxies altogether. Powerful outflows driven by active black holes can propel gas hundreds of thousands of light-years into intergalactic space. Over billions of years, the space between galaxies becomes enriched with heavier elements created inside stars. The relationship is reciprocal. Galaxies shape intergalactic space. Intergalactic space shapes galaxies. Neither exists in isolation. This interconnectedness represents one of the great intellectual transformations of modern astronomy. Earlier generations naturally focused upon individual celestial objects. Today's cosmologists increasingly focus upon relationships, matter flowing through filaments, energy influencing expansion, gravity linking structures across unimaginable distances. Nothing stands entirely alone. Even the great voids, which once seemed empty beyond significance, participate in this cosmic exchange. Their expansion influences neighboring filaments. Their low densities preserve clues about the earliest conditions of the universe. Their immense volumes amplify the effects of dark energy over cosmic time. The emptiest regions become indispensable for understanding the whole. There is a quiet elegance in this realization. Nature rarely separates its creations into isolated compartments. The atmosphere cannot be understood without the oceans. The oceans cannot be understood without the climate. Likewise, galaxies cannot be fully understood without the vast spaces surrounding them. The universe behaves less like a collection of disconnected objects and more like a single evolving organism, though one governed entirely by physical laws rather than biological purpose. As astronomers gradually embraced this wider perspective, they began noticing something even more surprising. Ideas that once belonged to entirely different fields of physics were beginning to converge. Black holes, dark matter, quantum fields, galaxy formation, cosmic expansion. What once appeared to be separate mysteries increasingly resembled different expressions of the same underlying universe. The deeper researchers looked, the more unexpected connections emerged, suggesting that the greatest discoveries might not lie within any single phenomenon, but in the relationships that quietly bind them all together. One of the most satisfying moments in science comes when ideas that once seemed unrelated begin to fit together. not because they become identical, not because one explanation replaces another, but because they reveal themselves as different parts of a much larger picture. Astronomy has experienced this kind of convergence many times. The motions of falling apples and orbiting planets were once separate mysteries until gravity united them under a single law. Electricity and magnetism were studied independently before they became two aspects of the same phenomenon more recently. The life cycles of stars became inseparable from the origin of the chemical elements that eventually formed planets and living organisms. The universe often rewards patience by revealing hidden connections. The mystery of intergalactic space has begun to do the same. At first, black holes appear to have very little in common with cosmic voids. One is almost unimaginably dense. The other is almost unimaginably empty. A black hole compresses enormous mass into an extraordinarily small region. A void spreads remarkably little matter across hundreds of millions of light years. They seem like opposites, yet both emerge from the same physical laws. Gravity creates them both. The difference lies not in the rules themselves, but in how matter is distributed. Where matter becomes overwhelmingly concentrated, gravity produces stars, galaxies, and eventually black holes. Where matter is initially sparse, gravity gradually pulls even more material away, allowing vast voids to grow larger over billions of years. The same force creates both extremes. This realization changes the way we think about the architecture of the universe. The brightest objects and the emptiest regions are not independent phenomena. They are complementary outcomes of a single cosmic evolution. The connection becomes even clearer when we follow the journey of matter itself. Consider a cloud of hydrogen floating through one of the filaments of the cosmic web. Over millions of years, gravity gently draws the gas toward a growing galaxy. The cloud becomes denser. Eventually, new stars ignite. Inside those stars, hydrogen fuses into helium. More massive stars continue the process, forging carbon, oxygen, silicon, and iron. When the largest stars reach the ends of their lives, they explode as supernovae, scattering these newly created elements back into space. Some of that material becomes part of future generations of stars. Some forms planets. Some drifts into intergalactic space once again. The same atoms may participate in this cycle repeatedly across billions of years. Nothing remains permanently confined. Matter circulates continuously between galaxies and the immense regions surrounding them. Even black holes, often portrayed as cosmic endings, participate in this exchange. As gas falls toward a supermassive black hole, not all of it disappears beyond the event horizon. Before crossing that boundary, enormous amounts of energy are released. Some of this energy drives powerful jets extending hundreds of thousands of light years into intergalactic space. These jets accelerate charged particles to extraordinary speeds and heat enormous volumes of surrounding gas. Rather than merely consuming matter, active black holes reshape the environments around entire galaxies. They regulate star formation. They influence the temperature of intergalactic gas. They alter how matter continues flowing through the cosmic web. In this way, one of the smallest regions in a galaxy can affect structures spanning millions of light years. The relationship works in both directions. Dense environments within the cosmic web provide fresh gas through galaxy mergers and gravitational interactions. The gas feeds central black holes, allowing them to grow larger. The black holes then return energy to the surrounding environment. The environment, in turn, influences the next generation of galaxies. The cycle continues. Nothing exists in complete isolation. Dark matter forms another essential connection. Although invisible, it provides much of the gravitational framework that guides the movement of ordinary matter. Galaxies form where dark matter concentrations become sufficiently dense. Filaments emerge because dark matter collapses into elongated structures under gravity. Even the positions of many galaxy clusters reflect this hidden scaffolding. Ordinary matter behaves rather like leaves floating upon a slowly moving river. The leaves are visible, the current beneath them is not. Yet the current determines where the leaves eventually gather. In much the same way, galaxies reveal the pathways carved by invisible gravitational influences. Another surprising connection appears through temperature. The space between galaxies is often imagined as uniformly cold. That expectation seems reasonable. Far from stars, little heat should exist. Reality proves more complicated. Some intergalactic gas reaches temperatures of tens of millions of degrees. This may sound astonishing until one remembers that temperature and density are different concepts. The gas is extraordinarily hot because individual particles move at tremendous speeds. Yet those particles are so widely separated that almost no heat could be transferred to a traveller passing through. One could drift through gas measuring millions of degrees while receiving almost no warmth at all. This curious combination of extreme temperature and extreme emptiness illustrates once again how unfamiliar intergalactic space truly is. It behaves according to physical laws that rarely resemble everyday experience. Even light itself participates in these unexpected relationships. As photons travel across billions of light years, they interact subtly with the matter and energy distributed throughout the cosmic web. Some wavelengths are absorbed, others scatter. Gravity gently alters their paths. The expansion of the universe stretches their wavelengths toward lower energies. By the time ancient light reaches Earth, it carries a detailed record of every significant encounter along its journey. Astronomers often describe the universe as a history book written in light. Perhaps it is equally accurate to think of it as a conversation. Every region of space leaves its signature upon the light passing through it. Galaxies speak. Clusters speak. Hydrogen clouds speak. Even the great voids contribute their own quiet influence. Taken individually, these effects appear subtle. Combined across billions of years, they become the evidence from which modern cosmology reconstructs the history of the cosmos. Perhaps the deepest connection of all concerns time. The cosmic web visible today did not always exist. Neither did galaxies. Neither did black holes. Nearly 14 billion years ago, all of these structures were still awaiting formation. The universe contained only the faintest differences in density. Differences so small that they are visible today only as delicate fluctuations in the cosmic microwave background. Everything that followed grew from those tiny beginnings. Every galaxy, every star, every planet, every black hole, every enormous void. The present complexity of the universe emerged gradually through simple physical laws acting patiently over immense spans of time. There is something profoundly reassuring about this realization. Nature does not require separate rules for every phenomenon. Again and again, the same underlying principles reveal themselves in new forms. Gravity shapes stars. Gravity shapes galaxies. Gravity shapes the cosmic web. Quantum fields influence the vacuum. The expanding fabric of space-time governs the largest distances. Each idea complements the others rather than replacing them. Yet despite these elegant connections, one profound challenge remains. The more astronomers unify their understanding of the universe, the more clearly they recognize the limits of present knowledge. Dark matter has not been directly identified. Dark energy remains mysterious. The quantum nature of space-time itself is still beyond complete understanding. Remarkably, many of the clues pointing toward these unanswered questions come not from the brilliant centers of galaxies, but from the immense, quiet darkness surrounding them. To continue the search, humanity has begun building instruments capable of observing the cosmos with greater precision than ever before, hoping that the next generation of discoveries may finally illuminate what the great spaces between galaxies have been quietly revealing all along. Every generation of astronomers inherits two universes. One is the universe they can already observe. The other is the larger universe that their instruments have not yet revealed. The history of astronomy is, in many ways, the gradual movement of the boundary between those two realms. Galileo's small telescope transformed faint points of light into worlds. Large reflecting telescopes revealed distant galaxies. Radio observatories uncovered phenomena invisible to human eyes. Space telescopes escaped Earth's atmosphere, allowing the cosmos to be viewed with unprecedented clarity. Each technological advance has carried the same quiet lesson. The universe has consistently proven richer than our previous observations allowed us to believe. The study of intergalactic space has followed precisely this path. Much of what astronomers now understand about the cosmic web would have been impossible only a few decades ago, not because the universe itself changed, because humanity finally developed the tools capable of seeing it more clearly. One of the greatest revolutions began above Earth's atmosphere. The Hubble Space Telescope, launched in 1990, became famous for its breathtaking images of galaxies and nebulae. Yet beyond its beauty, Hubble fundamentally transformed cosmology. By observing galaxies billions of light-years away, it allowed astronomers to examine different eras of cosmic history. Looking farther into space also means looking farther into the past. A galaxy observed 10 billion light-years away appears not as it exists today, but as it existed 10 billion years ago. The telescope therefore became something remarkable, not merely an observatory, a time machine, by comparing galaxies across different distances. Astronomers gradually reconstructed how cosmic structures evolved over billions of years. They observed younger galaxies appearing smaller, more irregular, and more actively forming stars than many nearby galaxies. These observations matched theoretical models suggesting that galaxies slowly assembled through mergers and continuous growth along the filaments of the cosmic web. The invisible framework predicted by simulations appeared increasingly consistent with reality. Yet Hubble could not observe everything. Some of the most important clues lie beyond visible light. This led astronomers to expand their view across the entire electromagnetic spectrum. Radio telescopes became especially valuable. Hydrogen, the most abundant element in the universe, emits radio waves at a characteristic wavelength of 21 centimeters. Although individual hydrogen clouds between galaxies are extraordinarily faint, enormous radio arrays can gradually detect their presence. Facilities such as the Very Large Array in New Mexico and more recent Pathfinder instruments for the upcoming Square Kilometre Array have begun tracing diffuse hydrogen across intergalactic space with steadily improving sensitivity. These observations help reveal how gas flows from the cosmic web into galaxies. Rather than existing as isolated systems, galaxies continuously exchange matter with their surroundings. Fresh hydrogen streams inward through filaments. Meanwhile, energetic processes inside galaxies return enriched gas back into intergalactic space. The relationship is dynamic. The boundaries are remarkably porous. X-ray astronomy opened another window. Between galaxies inside massive clusters lies gas heated to tens of millions of degrees. Such temperatures produce almost no visible light but emit strongly in X-rays. Observatories including Chandra and XMM Newton have mapped these enormous reservoirs of hot plasma. Remarkably, the total mass of this gas often exceeds the combined mass of all the visible stars within the cluster. What once appeared to be empty space is revealed instead as a vast ocean of extremely diffuse, extraordinarily hot matter. Still, even these discoveries account for only part of the ordinary matter expected from cosmological models. For years, astronomers confronted what became known as the missing baryon problem. The term sounds mysterious, but its meaning is straightforward. Calculations based on the early universe indicated how much ordinary matter, composed of protons and neutrons, should exist today. Yet inventories of stars, galaxies, and hot cluster gas consistently fell short. A substantial fraction appeared to be missing, not missing in the sense that it had vanished. Missing because astronomers had not yet found it. Gradually, evidence pointed toward an answer. Much of the ordinary matter appears to reside within the warm-hot intergalactic medium, often abbreviated as the WIM. This material is astonishingly diffuse. Its density is so low that detecting it directly requires extraordinarily sensitive observations. Temperatures range from roughly 100,000 to 10 million degrees. Despite these extreme temperatures, the gas remains almost invisible because it is spread so thinly across immense distances. Finding it resembles trying to detect a faint mist stretching across an entire continent. Recent observations using X-ray spectroscopy and ultraviolet measurements have provided increasingly convincing evidence that this elusive medium contains a significant fraction of the previously missing ordinary matter. The universe, it seems, had been quietly hiding much of its familiar material between galaxies all along. Computer simulations have advanced just as dramatically as telescopes. Modern supercomputers now recreate enormous virtual universes containing billions of particles representing both dark matter and ordinary matter, beginning shortly after the Big Bang. These simulations evolve according to the known laws of physics. Gravity gathers matter, gas cools, stars ignite, galaxies merge, the cosmic web gradually emerges. One of the most influential examples is the illustrious TNG simulation. Rather than merely producing attractive visualizations, simulations like illustrious TNG generate detailed predictions that astronomers can compare directly with observations. Do galaxies form at the correct rates? Do clusters possess the expected masses? Do voids expand as observations suggest? Agreement strengthens confidence. Disagreement reveals where current theories require refinement. In this way, simulations have become laboratories for cosmology. Researchers cannot experiment with the real universe. They can, however, explore different physical assumptions inside carefully constructed virtual ones. Perhaps the most transformative observatory of recent years has been the James Webb Space Telescope. Although designed primarily to observe infrared light, Webb has already begun revealing galaxies that formed surprisingly early in cosmic history. Its observations are providing fresh information about how rapidly the first stars and galaxies assembled after the Big Bang. Some early results have sparked lively scientific discussion because they appear more complex than many researchers expected. Importantly, this does not mean existing cosmological models have been overturned. Rather, it illustrates how new observations continually refine scientific understanding. The universe rarely conforms perfectly to our first expectations. Instead, it invites continual improvement. Ground-based observatories are joining this effort on an unprecedented scale. The VRC Rubin Observatory, with its enormous survey capabilities, is expected to map billions of galaxies over the coming years. Such observations will allow astronomers to study dark matter through weak gravitational lensing with far greater precision than ever before. Meanwhile, the Euclid Space Telescope is surveying billions of galaxies across much of cosmic history, seeking to understand both the distribution of dark matter and the nature of dark energy. Each new mission contributes another layer to an increasingly detailed portrait of the universe. What is striking is not simply the quantity of data now being collected, it is the remarkable convergence of independent methods, infrared telescopes, radio observatories, X-ray satellites, galaxy surveys, gravitational lensing measurements, supercomputer simulations. Together they are revealing that the space between galaxies is not an empty backdrop, but one of the richest scientific frontiers in existence. And yet, for all this extraordinary progress, modern astronomy has reached an unexpected conclusion. The more precisely we observe the cosmos, the more clearly we can define the questions that remain unanswered. Our maps have become astonishingly detailed. Our instruments have become astonishingly sensitive. But some of the deepest mysteries have only grown sharper. The greatest discoveries of the coming decades may not come from finding something entirely new. They may come from finally understanding why so much of the universe continues to hide in plain sight. Within the vast and seemingly silent darkness between the galaxies, there is a quiet difference between what science knows and what science understands. Knowledge grows through observation, understanding grows through explanation. Sometimes the two advance together, at other times, observations race ahead while explanations struggle to keep pace. Astronomy has entered one of those remarkable periods. Never before have human beings possessed such detailed maps of the universe. Never before have we measured cosmic distances with such precision. Never before have we observed galaxies whose light began its journey only a few 100 million years after the Big Bang. And yet, despite these extraordinary achievements, some of the most fundamental questions remain unanswered. Perhaps this should not surprise us. The farther we extend our view into the cosmos, the larger the horizon of ignorance becomes. Every answer reveals another question waiting just beyond it. The mystery of intergalactic space illustrates this beautifully. Astronomers have established with considerable confidence that galaxies trace an immense cosmic web. They have measured the accelerating expansion of the universe. They have detected the gravitational influence of invisible matter. They have found diffuse gas stretching between galaxies. They have even reconstructed the earliest fluctuations from which today's structures emerged. Yet beneath this impressive framework lies an uncomfortable truth. Much of what governs the larger scales of the universe remains unidentified. Dark matter is perhaps the clearest example. Its gravitational influence appears almost everywhere astronomers look. Galaxy rotation curves, galaxy clusters, gravitational lensing, the cosmic microwave background. The growth of large-scale structure. Each provides independent evidence pointing toward additional unseen mass. Taken together, the observations are remarkably persuasive, but evidence for an effect is not the same as identifying its cause. After decades of increasingly sophisticated experiments, no dark matter particle has been conclusively detected. Underground laboratories have searched for rare interactions. Particle accelerators have explored new energy ranges. Sensitive detectors have monitored the faintest possible signals. Each generation of experiments has improved upon the last. Each has narrowed the possibilities. Yet the identity of dark matter remains elusive. This does not weaken the observations themselves. Galaxies still behave exactly as they always have. Rather, it reminds us that nature has revealed the existence of something before revealing what that something is. History offers many similar examples. Neptune was inferred through its gravitational influence before anyone observed it directly. The neutrino was proposed long before experiments confirmed its existence. In science, effects are often recognized before their underlying causes become fully understood. Dark energy presents an even greater challenge. Unlike dark matter, which attracts through gravity, dark energy appears to influence the expansion of the universe itself. Its effects become noticeable only across enormous distances. Closer to home, gravity still dominates. The solar system remains stable. Galaxies remain gravitationally bound. Even galaxy clusters resist the expansion within their own boundaries. Only on the larger scales does dark energy gradually reveal its presence. And there lies the mystery. Why does it exist at all, if it truly represents the energy of empty space? Why does it possess exactly the tiny value that observations suggest? Not slightly larger, not slightly smaller. The measured value allows galaxies, stars, and planets to form over billions of years. Many theoretical calculations, however, predict a vacuum energy enormously greater than what astronomers observe. The disagreement is so vast that physicists often describe it as one of the largest mismatches between theory and observation in all of science. No accepted explanation yet bridges that gap. Another unanswered question concerns the earliest moments of cosmic history. The cosmic microwave background provides a remarkably detailed picture of the universe approximately 380,000 years after the Big Bang. Before that time, the universe remained opaque to light. Earlier events must therefore be reconstructed indirectly. Inflation, the idea that the infant universe underwent an extremely rapid period of expansion, explains many observed features with impressive success. It naturally accounts for the remarkable uniformity of the cosmos, while also providing a mechanism for generating the tiny fluctuations that later grew into galaxies and the cosmic web. Yet inflation itself remains an active area of research. Many versions of the theory exist. Astronomers continue searching for observations capable of distinguishing among them. The broad concept enjoys substantial support. Its precise physical mechanism remains uncertain. Even the cosmic web still contains unanswered questions. Simulations reproduce its overall appearance remarkably well, but the detailed behavior of gas, magnetic fields, and galaxy formation within the filaments remains extraordinarily complex. How efficiently does gas flow into galaxies? How much material do black holes return to intergalactic space? How do magnetic fields evolve across hundreds of millions of light years? Researchers continue refining their models as new observations become available. The story grows richer rather than simpler. Then there is the question of the vacuum itself. Quantum field theory successfully predicts countless experimental results with astonishing accuracy. General relativity describes gravity across enormous scales with equal elegance. Yet the two theories remain mathematically difficult to unite into a single comprehensive framework. Inside black holes, near the earliest moments of the Big Bang, perhaps even within the deepest properties of empty space, a complete theory of quantum gravity has not yet been achieved. Without it, our understanding of space-time itself remains incomplete. There are also mysteries born not from theory, but from observation. For example, astronomers continue measuring the current expansion rate of the universe using different techniques. One method relies on nearby galaxies and standard candles such as Cepheid variable stars and Type Ia supernovae. Another derives the expansion rate from observations of the early universe, encoded in the cosmic microwave background. Both methods are highly sophisticated. Both have been refined repeatedly. Yet they currently produce values that differ by more than expected from their estimated uncertainties. This discrepancy has become known as the Hubble tension. Scientists are actively investigating whether it reflects subtle measurement effects, incomplete understanding of astrophysical processes, or perhaps entirely new physics. At present, no consensus exists. The question remains open. What makes these mysteries so compelling is not that they undermine modern cosmology. On the contrary, they arise because cosmology has become extraordinarily precise. Small discrepancies matter precisely because the broader framework explains so much else. When measurements become accurate enough, even tiny inconsistencies deserve careful attention. History shows that such inconsistencies sometimes lead to profound discoveries, or they simply improve existing theories. Science welcomes either outcome. There is another lesson hidden within these unanswered questions. Uncertainty is not a weakness of science. It is one of its defining strengths. Astronomers openly distinguish between observation and interpretation, between established evidence and promising hypotheses, between confidence and certainty. Doing so allows knowledge to evolve without abandoning what has already been firmly established. Perhaps nowhere is this more evident than in the great spaces between galaxies. A century ago, they were largely ignored. Today, they have become one of the most important laboratories in cosmology. They contain clues about dark matter, about dark energy, about galaxy formation, about the earliest moments of the universe, and perhaps about the nature of space-time itself. The emptiest places in existence have become the richest in unanswered questions. The challenge now is no longer recognizing that these mysteries exist. It is discovering whether our current tools are capable of solving them, or whether entirely new ways of observing the universe will be required before the silence between the galaxies finally begins to yield its deepest secrets. Every scientific instrument carries within it an invisible boundary. Beyond that boundary, nature continues exactly as before, but human knowledge becomes uncertain. A microscope eventually reaches structures too small to resolve. An ocean expedition encounters depths beyond the reach of sunlight. A spacecraft traveling outward eventually loses contact with Earth. Astronomy is no different. No matter how powerful a telescope becomes, there comes a point where the universe simply grows too faint, too distant, or too subtle to observe directly. The study of intergalactic space has now reached one of those frontiers. It is not that astronomers have run out of questions. Quite the opposite. The questions have become so precise that answering them demands measurements approaching the very limits of what the laws of physics allow. One obvious challenge is distance. Light, despite traveling faster than anything else in nature, requires time. A great deal of time. When we observe a galaxy 10 billion light-years away, we do not see it as it exists today. We see it as it appeared 10 billion years ago. The farther we look, the younger the universe becomes. Eventually, this creates an unavoidable barrier. Before approximately 380,000 years after the Big Bang, the universe was filled with an extremely hot plasma. Electrons and atomic nuclei moved freely, scattering photons in every direction. Light could not travel uninterrupted. The universe was opaque. No optical telescope, regardless of its size, can directly observe through that ancient fog. The cosmic microwave background marks the oldest light that has reached us. Beyond it lies a chapter of cosmic history that cannot be viewed using ordinary electromagnetic radiation. Astronomers must instead search for indirect evidence. Gravitational waves, neutrinos. Perhaps one day entirely new observational methods. The earliest history of the universe remains hidden not because humanity lacks determination, but because nature itself placed a curtain across those first moments. Intergalactic space presents another, more subtle limitation. Its greatest structures are astonishingly diffuse. A galaxy shines because billions of stars concentrate enormous amounts of energy into a relatively small region. The warm gas between galaxies does not. Its atoms are separated by enormous distances. Its glow is exceedingly faint. Detecting such material often requires observing for hundreds of hours with highly specialized instruments. Even then, astronomers frequently rely on statistical analysis rather than direct imaging. This creates an unusual situation. Sometimes researchers become more confident about a structure they cannot clearly photograph than about one they can. Confidence comes not from appearance, but from repeated measurements obtained through different techniques. In cosmology, patience often substitutes for brightness. Dark matter presents an even greater observational challenge. Everything known about it comes from its gravitational influence. No telescope has ever recorded dark matter emitting visible light. No radio antenna has received dark matter signals. No X-ray observatory has photographed dark matter clouds. Its presence is reconstructed entirely through its effects upon ordinary matter and space-time. This raises an intriguing philosophical question. Can something remain scientifically real if it has never been observed directly? Science answers with remarkable consistency. Yes, provided its effects are measurable, reproducible, and accurately predict future observations. The wind itself cannot be seen, only leaves moving beneath it. Gravity cannot be viewed directly, only the motion of planets and the bending of light. Likewise, dark matter reveals itself through consequences rather than appearance. Still, astronomers naturally seek direct confirmation. Numerous underground laboratories continue searching for interactions between dark matter particles and ordinary matter. These experiments operate beneath mountains or deep underground to shield their detectors from cosmic rays and other background radiation. Their sensitivity has improved enormously. Each generation excludes additional possibilities, yet the silence continues. Every null result is valuable. It tells researchers where dark matter is not, but the answer to where it is remains incomplete. Dark energy introduces an entirely different limitation. Unlike dark matter, which gathers within galaxies and clusters, dark energy appears remarkably uniform. Its effects emerge only across enormous cosmic distances. Individual galaxies reveal almost nothing about it. Instead, astronomers must observe millions of galaxies distributed across billions of light years, searching for tiny statistical differences in how the universe expands. The measurements demand extraordinary precision, a slight calibration error, a subtle instrumental effect, an unnoticed property of distant supernovae. Any of these could influence conclusions if not carefully understood. Modern cosmology therefore depends as much upon careful data analysis as upon telescope design. The frontier has become mathematical as well as observational. Computer simulations face their own boundaries. Today's supercomputers perform calculations involving billions or even trillions of interacting particles. These simulations reproduce many observed features of the universe with remarkable realism. Yet no simulation includes every physical process in complete detail. Approximations remain necessary. Star formation, magnetic fields, supernova explosions, the behavior of gas around black holes. Each involves physical scales far smaller than the simulation can directly resolve. Researchers therefore develop sophisticated mathematical models describing how these unresolved processes influence larger structures. As computing power grows, those approximations steadily improve. Even so, every simulation remains a conversation between theory and observation, rather than a perfect replica of reality. Another frontier lies in time itself. Human civilization has observed the heavens systematically for only a tiny fraction of cosmic history. A century of modern astronomy seems impressive from our perspective. For the universe, it scarcely qualifies as a moment. Many cosmological processes unfold so slowly that direct observation of their evolution becomes impossible within a human lifetime. Astronomers compensate by studying different objects at different stages of development. Young galaxies, mature galaxies, ancient galaxies. Together they reconstruct a sequence much as a botanist might study seeds. Saplings, mature trees, and decaying forests to understand the complete life cycle of a species. The method is powerful. It is also indirect. The frontier therefore involves not only seeing farther, but learning how to interpret what cannot be watched unfold in real time. Perhaps the deepest boundary concerns theory itself. General relativity describes gravity with extraordinary success across astronomical distances. Quantum mechanics describes the microscopic world with equal precision. Each has survived countless experimental tests. Yet together they resist complete unification. Near the centers of black holes, during the earliest instants after the Big Bang, possibly even within the deepest structure of empty space, both theories become simultaneously important. No complete framework yet joins them seamlessly. Many physicists suspect that solving this problem will transform our understanding of space-time itself. Whether that transformation will also illuminate the mysteries of intergalactic space remains unknown. History suggests caution. The greatest scientific revolutions rarely arrive exactly where researchers expect them. Radio astronomy revealed entirely new classes of celestial objects. The cosmic microwave background was discovered while engineers were attempting to eliminate unwanted noise from a communications antenna. Gravitational waves, once considered almost impossible to detect, are now routinely observed. Progress often begins with careful measurements rather than dramatic revelations. The frontier of knowledge is therefore less like a wall than a slowly retreating shoreline. Each new observation pushes it outward a little farther. Beyond it stretches another ocean of unanswered questions. The vast darkness between galaxies occupies much of that ocean today. It challenges our instruments. It tests our theories. It reminds us that even after centuries of astronomy, the largest part of the observable universe remains only partially understood. And perhaps the greatest challenge is not merely reaching farther into that darkness. It is recognizing that the answers waiting there may fundamentally reshape the way we understand reality itself. Just as previous generations were forced to reconsider their place in a universe far larger and stranger than they had ever imagined. There are moments in science when a discovery does more than answer a question. It changes the meaning of questions themselves. The realization that Earth orbits the Sun didn't simply rearrange the solar system. It transformed humanity's understanding of its place in the cosmos. The discovery that galaxies exist beyond the Milky Way did not merely add more stars to the universe. It expanded the scale of existence beyond anything previously imagined. The study of intergalactic space may represent another transformation of this kind. Not because it introduces entirely new laws of physics, not because it overturns everything already known, but because it quietly changes what we believe the universe actually is. For centuries, matter occupied the center of scientific attention. The history of astronomy naturally followed the objects that could be seen. Stars, planets, comets, nebulae, galaxies. These luminous structures became the landmarks by which the universe was understood. Space itself seemed secondary. It separated objects without contributing much of its own. Modern cosmology has gradually reversed that perspective. Today, matter appears almost like islands scattered across an ocean whose properties increasingly determine the fate of the entire landscape. This shift is subtle, yet profound. Consider an ordinary map of Earth. At first glance, the continents appear to define the planet. Cities, mountains, and forests capture our attention. The oceans seem like the empty regions between them. Yet Earth's climate, weather, biological diversity, and even the movement of continents are deeply influenced by those oceans. Remove the oceans, and the continents themselves become almost unrecognizable. The spaces between them were never passive. They were essential. The same principle appears to apply to the universe. The great expanses between galaxies are not merely distances waiting to be crossed. They influence how galaxies form. They regulate how matter flows through the cosmic web. They preserve clues about the earliest universe. They dominate the expansion of space-time itself. The background has quietly become one of the principal actors. This realization encourages an entirely different way of thinking. Instead of asking where galaxies exist, astronomers increasingly ask how galaxies interact with their environment. Instead of studying isolated objects, they examine relationships. Matter flowing through filaments, gas cycling between galaxies and intergalactic space, gravity linking structures across hundreds of millions of light years. Nothing stands completely alone. Everything belongs to a larger network. Perhaps this explains why cosmology has become one of the most interdisciplinary sciences. Astronomers study galaxies. Particle physicists investigate dark matter. Quantum theorists explore the properties of the vacuum. Relativists describe the geometry of space-time. Computer scientists build simulations containing billions of interacting particles. Engineers design instruments capable of detecting signals almost indistinguishable from noise. Each discipline contributes one piece of a puzzle that none could solve independently. The universe itself refuses to separate neatly into academic subjects. Nature does not recognize departmental boundaries. One of the most striking consequences of this broader perspective concerns scale. Human beings naturally think of size in physical dimensions. Large mountains, wide oceans, immense galaxies. Yet cosmology suggests another kind of scale. Scale of influence. A supermassive black hole contains extraordinary density. Its direct gravitational influence extends across only a tiny fraction of its host galaxy. By contrast, dark energy possesses an extraordinarily small energy density. Locally, its effects are essentially undetectable across billions of light years. However, it shapes the evolution of the observable universe. The most concentrated phenomena are not always the most influential. Sometimes the gentlest effects become dominant simply because they operate everywhere. This lesson appears repeatedly throughout nature. A single raindrop changes almost nothing. The global water cycle shapes entire continents. An individual molecule of oxygen is insignificant. Earth's atmosphere makes complex life possible. Likewise, the physical properties of empty space may seem negligible within a laboratory, yet become decisive across cosmic distances. Magnitude depends upon context. The universe continually reminds us of this. Another implication concerns simplicity. Many of the most beautiful scientific ideas arise not because nature is complicated, but because simple principles acting patiently produce astonishing complexity. Gravity attracts matter. That statement fits comfortably within a single sentence. Yet given nearly 14 billion years, gravity alone helps generate galaxies, clusters, filaments, and enormous voids. Likewise, the expansion of space-time follows elegant mathematical rules. Those rules eventually produce an observable universe spanning tens of billions of light years. The complexity we observe often emerges from remarkable simplicity sustained across immense stretches of time. This perspective also changes how we think about emptiness itself. Language naturally encourages us to regard empty space as the absence of something, but physics increasingly describes the vacuum through what it possesses rather than what it lacks. Geometry, quantum fields, energy, curvature, expansion. These are not objects occupying space. They are properties of space. The distinction matters. A desert is defined by what is missing. A climate is defined by what is present. Modern cosmology increasingly treats the vacuum more like the latter than the former. This does not mean every mystery has been solved. Far from it. Researchers continue debating the nature of dark energy. They continue searching for dark matter particles. They continue attempting to unite quantum mechanics with general relativity. Scientific uncertainty remains substantial, yet uncertainty itself has become more focused. A century ago, Astronomers did not know which questions to ask about intergalactic space. Today, they ask remarkably precise ones. How does dark matter behave on the smallest scales? Does dark energy remain constant throughout cosmic history? Can gravitational waves reveal previously inaccessible regions of the early universe? What is the quantum structure of space-time? Progress often begins when vague curiosity becomes a clearly defined question. Perhaps the deepest implication concerns humanity. For most of history, civilizations naturally measure themselves against nearby landscapes, mountains, rivers, oceans, eventually against planets and stars. Modern cosmology asks us to think in terms of structures spanning billions of light years, most of whose volume appears almost empty. Such scales do not diminish humanity. Rather, they reveal something remarkable about human curiosity. Creatures occupying a small rocky planet orbiting an ordinary star have learned to infer invisible matter, detect the oldest light in existence, and reconstruct the growth of structures extending across much of the observable universe. That achievement is extraordinary, not because it represents the end of discovery, because it almost certainly represents only the beginning. Each generation inherits better instruments, richer observations, and deeper questions than the one before. The silence between galaxies has already transformed our understanding of the cosmos once. There is every reason to believe it will do so again, for if the largest, quietest regions of the universe continue to challenge our theories, then perhaps the next great revolution in physics will not emerge from the brilliant heart of a galaxy or the violent edge of a black hole. Perhaps it will arise from the patient study of the vast darkness that, for so long, humanity mistook for nothing at all. Every story about the universe eventually becomes a story about time. Stars are born, shine for millions or billions of years, and eventually fade. Galaxies collide, merge, and slowly reshape themselves. Black holes grow as they consume gas and stars, while others remain almost unchanged for unimaginable ages. Nothing in the cosmos is truly permanent, yet when astronomers attempt to look far beyond the present, into trillions of years that no civilization will ever witness directly, they must proceed with great care. Unlike the past, which leaves evidence behind, the future cannot be observed. It can only be explored through the laws of physics as we currently understand them. That distinction matters. Everything that follows is not a prediction carved into certainty. It is an exploration based upon the best available evidence, always subject to revision should future discoveries reveal new physics. Within that framework, however, a remarkably coherent picture begins to emerge. The first thing to understand is that the expansion of the universe is expected to continue. Current observations indicate that dark energy dominates the large-scale evolution of the cosmos, if its properties remain approximately constant, as the standard cosmological model suggests. Then the distance between galaxy clusters will continue increasing indefinitely. This does not mean that every object drifts apart. Gravity still wins wherever enough matter is gathered. The Milky Way and Andromeda, for example, remain on course to merge because their mutual gravity easily overcomes the gentle expansion of space across such relatively short distances. The same is true for many galaxy groups and clusters. They remain gravitationally bound. Beyond those local neighborhoods, however, the picture changes. Clusters that are not already bound together will slowly separate. The cosmic web itself will become increasingly stretched. Filaments connecting distant superclusters will grow longer and thinner. The enormous voids between them will continue expanding. The architecture of the universe will not disappear. It will become progressively more isolated. To appreciate this future, it helps to think not in terms of objects moving rapidly through space, but of the space between them quietly increasing. There is no great explosion, no sudden tearing apart, only an almost imperceptible stretching that accumulates over billions upon billions of years. Each year the change is unimaginably small. Across trillions of years it becomes profound. Future observers living within our local group would witness a very different sky. By then, the Milky Way and Andromeda will have merged into a single giant elliptical galaxy, sometimes informally called Milkomeda. countless generations of stars will have formed and died within it. Its central black hole will likely have grown substantially through repeated mergers and the gradual accumulation of matter. Yet the most striking difference may lie beyond its boundaries. Many of today's familiar galaxies will no longer be visible, not because they have ceased to exist, not because their stars have gone dark, but because the expanding fabric of space will have carried them so far away that the light they emit after a certain point will never again reach us. They will slowly fade beyond the observable horizon. This horizon deserves careful explanation. It is not a physical wall surrounding the universe, nor does it represent the edge of existence. Instead, it marks the limit imposed by the finite speed of light combined with the ongoing expansion of space-time. Beyond that limit, events may continue exactly as before. They simply become permanently inaccessible to observation. In an expanding universe dominated by dark energy, this horizon gradually becomes more restrictive. Future civilizations may inhabit a cosmos appearing vastly smaller than the one we observe today. Ironically, they could possess more advanced technology than ours while having access to less observable evidence. The distant galaxies that allowed 20th and 21st century astronomers to discover cosmic expansion might no longer be detectable. Without those observations, reconstructing the true history of the universe could become extraordinarily difficult. Some cosmologists have pointed out this fascinating possibility. The best era for studying the large-scale universe may, in some respects, be the present one.